Yes, hello together. Well, since I'm alone here in the lecture hall, next time I will just post in Moodle that you just announce if you want to come or not. I promised you that I also give parallel the lecture online, so it's just up to you. But in case that no one shows up, then it's easier for me to go just in my office and then I will give from there the online lecture. Okay, so we have started talking about estimating and especially confidence intervals the last time, but I think there was also one exercise left from the last time, and with this we will start today. So, and this was the mean squared error. This was, I think, no, not this, this one. So this was this part here, and there I was last time lost because, yeah, there were too much brackets, so to speak. So then, let's go here and we will start. So mean squared error equals the expected value of our estimator minus variable squared. And first of all, we just evaluate here our square. And you have to keep in mind that the expectation operator is still around the brackets. So we have here then theta hat squared plus 2 theta minus, sorry, theta hat squared plus theta squared. And then, since we have a linear operator, we can write expected value of theta hat squared minus expected value of 2 theta hat plus expected value of theta squared. Well, since this is our parameter we are looking for, we can treat this, of course, as a fixed number, and so we can take it out of the expectation operator. So we obtain E of theta hat squared minus 2 theta E of theta hat plus theta squared. And well, then we are doing something what we quite often do in mathematics, we just add a zero in a proper way. So here is a squared missing, because then we write expected value of theta hat squared, and now minus bracket expected value of theta hat, close bracket and close bracket, and then the squared outside, plus the same thing, so this is just adding a zero, and then we are left with these two terms, minus theta e of theta hat plus theta squared. Well, and now look at this. How can we write this? If we just define, for example, e of theta hat is a and theta is b, then this would be a squared minus 2ab plus b squared. And this is, how can we write this? I think this you know from school. Yes, great. A minus b squared. And so we write here e of theta hat minus theta squared is this. Why do we do this? Well, let's just look in our exercise. This was this. Actually, I can take this out, or oop. Let's cut this up. Hmm? Copy. And so, and what we see is, in this case, we already have our bias. And now we have to show that this is just the variance. of theta hat. And for this, we remember what is the definition of the variance. Variance of x equals e of x minus expected value of x squared. And if we evaluate also the square, we obtain e of x squared minus 2x e of x plus e of x in brackets squared. Again, linear operator. This is c of e of x squared minus e of 2x e of x plus e of x squared. Again, with the same argumentation, we took these two parameters outside the expected value operator. We can also take, sorry, not these two, but the two, oops, the 2 and the e of x, because of course taking 2 times the expected value operator is the number itself. So we obtain e of x squared minus 2 e of x in brackets squared plus e of x in brackets squared. Then we have here and here the same. So in the end, we obtain e of x squared minus e of x squared. And now we see that this is the same as we have here if we set x equals theta hat. And so we can just state that the mean squared error equals the variance biased via the squared difference between the expected value of our estimator theta hat and the unknown parameter theta. So this was from last time. But now we want to go back to our confidence intervals. And there we just started. Let me recapitulate this, that we, for example, ask, we have an estimator, x squared, and we are looking for the true parameter, x, or in our case, theta, and we want to know in which interval can we suppose the true parameter theta A and theta B with some given probability of alpha. So with the probability alpha, this interval centered via the via our estimator x bar covers with our given probability alpha the true parameter x. And this area depends, of course, on the distribution which is underlying our experiment. And quite often, we can assume that approximately our random variables xi are standard normally distributed, and especially we can say that we have a sample larger than 30, that then we can in general assume that our parameters are normally distributed. And of course, this I stated also last week, that our sample size, small n, has to be much smaller than the size of the parent distribution. And roughly we can say if this proportion is less than 5%, then we can approximately assume that we can use the normal distribution. But if this is not the case, especially if we have small random samples, less than 30, then we can show that our mean is not anymore. Oops, where is this gone? No. That then our random sample, our mean is not anymore standard normal distributed, but it is so-called t-distributed. And from this t-distribution, we can see that the larger the number of the sample size is, the closer we are at the normal distribution. Well, and so if we want to calculate our confidence intervals, we can then from the standardization, remember z equals x minus mu over sigma, we obtain the limits of the confidence intervals. And then, of course, we also have to keep in mind that the variance of our mean is scaling with the square root of n. And I think this we also just shortly recapitulate why this is the case, because this is also one of the central results, because this means if this is scaling with 1 over square root of n, this means that we become better and better and better with our estimation the larger our sample size. So we want to calculate the variance of the mean x bar, and then we just write what is this? Variance of 1 over n sum over xi, I from 1 to n. Now we can take this out of the variance, but remember, this is not taken out linearly, but we have to take it out with a square. So we obtain 1 over n squared variance of sum xi, I from 1 to n. And now our assumption, all xi are identical and independent distributed. Then this means that we can move the variance operator into the sum. 1 over n squared sum 1 to n variance of every single xi. But also they are identical distributed. So this is just the variance of our random variable. And this is a fixed number. And what is the sum of a fixed number from I from 1 to n? Or let's say sum over 3 from I from 1 to 4. What is this? This means 3 for I is 1 plus 3 for I is 2 plus 3 for I is 3 plus 3 for I is 4. So what does we have then here? So this would be 3 plus 3 plus 3 plus 3. I is 1, I is 2, I is 3, I is 4. So this would be 12. And if our sum goes up to the number n, and we have here just some one, any number you can think of, then we have to sum up n times a. Okay? So this would mean this is n times a. And if this is also just a fixed number, then we obtain 1 over n squared times n times sigma. This cancels, and sigma squared, and we obtain sigma squared over n equals the variance of the mean. And if we take, of course, the square root, then we obtain sigma x bar equals sigma x over square root of n. Hopefully you have seen this already in your introductory courses. Because this is more or less, the central result why it is a good idea to draw a larger random sample. Because then our confidence interval becomes smaller and smaller and smaller, the larger we take our sample. Okay, then we want to do some exercises. And let's cut this. Let me keep this in mind. Oops. Let's take this a bit smaller. You can still read this? So I think so. So what is the question? We have a random sample larger than 30. In our case, n is 625. Our parent distribution, our parent population is 100,000. Then, of course, we can say 625 over 100,000 is less than 5%. So we can take the standard normal distribution. We should have now these 625 wheels, and this we are testing. And on average, the mileage of these wheels is 36,000 kilometers. But of course, one wheel has a mileage of, let's say, 37,000, another one of 35,000, another one of 34,500, and another one of 40,000. So we should have a standard deviation of 48,000 kilometers. So more or less you would say the mileage of our wheels is 36,000 plus minus 48,000 kilometers. This is, just the first purely descriptive result which we can draw from our random sample. But now we want to know which interval covers the true mileage, because we don't know what is the expected value. If it's really 36,000, we don't know, because the parent distribution is, of course, much larger. And we want to know which interval covers the mileage of the parent distribution with a probability of 95%. And for this, we take this formula here. So theta A, the lower limit, just equals x bar, our estimator, minus z, standard deviation, over square root of n. So, and what do we have to insert for our variables here? X bar is, of course, of course, 36,000. And set, we need from this given confidence level of 95%. 1.96, great. And for this, I really recommend that you take this diagram in mind. Standard normal distribution means that we are looking for the interval where this area here, standard normal distribution, that this interval is 95%. And this we had some lectures before. Up. Let's take this again. Where do I have it? Here. So we have here 95, and the lower side is minus 1.96, and the upper side is plus 1.96. Or let's go in our table that you also see this. Was immer. Wischt. So now you should see the table. What's she doing now? Hoppala. We need the standard normal distribution. This is here. So how do we find in this table the 1.96? Which number we have to look for? Our confidence level is 95%. Here we have from the property of that the standard normal distribution is symmetric, all positive numbers. So the nicht, so what we have here is then this part would be just half of it. So up to here, this would be then 97.5%. Oh, so what we have to look for is within our table the number which corresponds to 0.97. And here we find it at this point, and we are happy. This is 1.9, and the second digit is a 6 here. So from this, we obtain that we have to insert for our Z 1.96, and then sigma hat 4,800 over square root of n 625. And why do I chose 625? Of course, because it is the square root just 25. So we obtain 36,000 minus 1.96 times 48 over 25, and this would be roughly 36,000 minus 1.96 times 48 over 25. So 35,623. 35,623 kilometers, and the upper limit would be what do we have to calculate? because now we have only the lower limit. Well, you do not. Yes, of course. Great. So just, oops. There we are. Where is my slide? And there. We have here just our plus sign. So 36,000 plus 1.96 times 48 over 25. And this would be then just inserting here our plus. And we obtain 36,376. 36,37,6. Well, and actually here you also just see that we have cut off the last two digits because this should, of course, be an interval which is totally symmetric around 36,000. So what we actually have done here is that in the standard normal distribution, we have here minus 1.96. Here we have plus 1.96. That we translate this into our normal distribution, that this corresponds then theta A, and this corresponds then theta B. Let's do it symmetrically. And here f of x. So this was the first question. And now two really hard further questions. Yep. So what do we have to change? If we ask the same question, still confidence level 95%, but our sample size is increased to 2,500. What do I have to change? So only this parameter is changing. N, yes. So this is just this number here, the 625. Here we have to insert 2,500, and therefore we just obtain then lower limit is 36,000 minus 1.96 times 4,800 divided now by 50, because the square root of 2,500 is just 50. And in order that I do not have to write so much, I just write here for the upper and lower limit plus minus 1.96. And then we obtain theta A equals, oh, I have closed Excel. No, here. So now we just change up to 50, 36,188. This was theta B, 36,188. And the lower limit would be 35,811. 35,811 approximately, of course. And the last question. Uh, let's take blue. Now we should come back to our first size of our random sample, 625. Oh, here we are. Z is 2.58. And this just means that we have to change this here into 99. Still, we have our 625, but now we are moving to a confidence level which is larger. And of course, if we increase our confidence level, then of course our interval should be broadened. And this you should always also keep in mind if you're doing this, that at first you think of, okay, what is changing if I'm changing some parameters? That you not only just type in your calculator or in Excel and pressing enter, and then of course, well, there is some number, that you also have in mind what should happen. Should my number now larger or lower than a number which I have calculated before? So now we know that compared to the first question, we should have a larger interval. And the 2.58 we have here. And of course, if we go in our table, then now we should have here that we have to look to 0.995. And if we look this up, then we have approximately here 0.995, and this is the 2.5 here, and as I have to smaller. Oh, sorry, not this one. Oops. Here we are closer to 0.995 and the 8 up here. So we just insert at this part here 2.58, and we obtain 2AB equals 36,000 plus minus 48 over 25 times 2.58. And then we have theta A is roughly and theta B is roughly 2.58 and 25. 35,504. 35,504 and theta B plus 36,495. 36,495 kilometers. So I've done this quite slowly, but the idea behind this is that if I pose then another question, that you really can recapitulate this and you are really able to also calculate these confidence intervals. So, but now we are switching to a situation where we have a small sample. Let's say you, within your bachelor thesis or something like this, you want to know how much are your fellow students are working. But as it is quite often the case, you setting up something in the internet and not many of your colleagues are really answering. So you should have just a random sample size of n equals 16. We know that at the Yale University we have roughly 6,000 students, but from your sample size, 16 answers, we know that these people are roughly working 18.36 hours. What did I write per week? Plus minus standard deviation of 3.42. So now you want to calculate the confidence interval to a confidence level of 90%. But since now you have only a small random sample, you cannot take anymore the standard normal distribution, but you have to take the t-distribution. This means you have to take the t distribution, and in order that you are really allowed to take the t distribution, you also have to assume that the parent population is normally distributed. If you have a large sample size, then we have the central limit theorem, and you do not have to care about what is the distribution of your parent distribution. But now, if you have a small sample size, you really have to assume that your parent distribution is normally distributed. This you also have to keep in mind. But if this is the case, and this is the case, then you can take the t distribution. And the calculation of the confidence interval is still more or less the same as you see it here. But what you have to change is just the parameter from the distribution. Here we have inserted the parameter for 1.96, for example, for a confidence level of 95%. But now we have here to look up the number from the t distribution. Let's also take this. But now again we start. What we have already is theta A equals x bar in our case. Well, this is our estimator from our random sample. So 18.36 plus, minus the number from the t distribution. This we have to look up from our table or from your software package. But we have already the standard deviation, 3.42 over square root of n, square root of 16. And now we need Tn minus 1 to a level of 90%. Again, which number do we need? The t distribution is also symmetrically, I have shown you. So for a two-sided confidence interval, is symmetrically. For a two-sided confidence interval, again, we know that if this area should be 90%, then this area and this area has to be 5%. So of course, then we have to look up here the number for 0.95. And for this, we go now into the table of the t-distribution. This I also will upload for you. And we also know that the t-distribution becomes closer and closer to the normal distribution the larger the sample size, but the numbers are of course also dependent on the sample size. This was shown with the subscript n-1. So if we go into the table, then we have to take, as I explained, 95. This is here, maybe a bit larger. So then you see the 95. And we have a sample size of 16. So our t-value is 1.75 approximately. Okay? So times 1.75. Let's say here, this is sigma hat, this is n, and this is t n-1. So we have 18.36 times, minus 1.75 times 3.42 over square root of 16 is, of course, 4. So we obtain 16.86. Is roughly 16.86. And theta b, of course, we obtain to 18.36 plus 3.42 over square root of 16 times 1.75 is then roughly a plus here. 1986. And this is ours. So hopefully you really have seen that this is nothing really complicated, and this is always done in the same way. The only thing you have to change to the former case is that you have to look up or to calculate here a different number for the confidence level, because now the underlying distribution is not the normal distribution, but the t-distribution. And I think one last thing we also can do today, and this is the special case if you have a Bernoulli experiment. This means if you just have a dichotomous attribute, this means the outcome, outcome is only x equals 1 or x equals 0 or x equals 1. And in this case, remember that our variance was just square root of the probability times 1 minus the probability. If we go back here, did we had it? The random variable? Variance of no, this was then the other lecture. Oops. No, even one lecture before. Here, the binomial distribution. Variance is just np over 1 minus p. And if we take this for our confidence interval, where we are here. So remember, variance of p is just n times p hat minus 1 p hat. And what we need, this is sigma squared. And what we need is the standard distribution of the mean. So sigma over n. So we have to take here the square root and here also. And then you have square root of n p hat times n minus p hat over n. And if we take this n, oops, sorry. Oh, you see it still over n, then we obtain square root of n p hat 1 minus p hat over n squared. This cancels out, and in the end, we obtain p hat times 1 minus p hat over n. And this is just what we have here. So this, at a first look, quite complicated formula, we just obtain from our confidence interval with a normally distributed parameter, and we just inserting for our standard deviation sigma hat. So here, oops, over n equals. So, oh, so we are then at the end of our lecture today, and for Thursday, then you obtain another homework that you just, should take this formula now of a Bernoulli experiment of a dichotomous attribute, and we take the poll in the UK, and maybe you know that you have not only the Conservative and the Labour Party, but that you have in UK also a third party, the Liberal Party, which has roughly a size of around 10% of the votes, but they do not have, really something to say in UK, because in the UK, you know that from the voting system, only the guy comes to the House of Commons which has the most votes in his area. And therefore, all these guys with only 10% of the votes, they drop out of the system. But anyway, we have this party there, and we just say that we make also a random sample, that we ask 1,200 people, and 96 of these people would say that on Sunday maybe they will vote for the Liberal Party. And now we want to calculate the confidence interval of 95% from this random sample, which covers then the true proportion in the real vote, where you again can say that you have the total number of all voters in UK, which will be roughly about 40 or 45 million people. So just try to calculate this confidence interval, and of course you just have to apply this formula here.